Okay, this next transformation has to do with stretching graphs in the y direction. Imagine you've got a y equals x squared and you stretch it a little bit, it goes all long and skinny up the y-axis. This is what this next transformation is about. So here I go, the same sort of thing. I'm playing with y equals x squared as my general function. So that's y equals x squared. And this one, y equals 2x squared. That's that one. The next one along is y equals 3x squared. And the last one, y equals 4x squared. And that's what the spreadsheet produced for me. Of course, I had to type in the right numbers and drag fully around the place, so no problem there. So we're going to study how x squared gets transformed into 2x squared, and how x squared gets transformed to 3x squared and then 4x squared, and we'll see how it looks on paper. Quite horrific, and as is usual I tend to put blue around it. That's my general function, y equals some sort of function of x, and these are my three transformations I'm about to perform on the other page. Bam, and there they are. Now try not to be sick and don't run away from the video. Now let's identify the generic one, the one that's basically y equals x squared. Now easy to spot, when x equals 6, y equals 36. I think we managed to square it, so I reckon that's y equals x squared. Let's go back. Let's identify y equals 2x squared. Well, let's have a look. I'm looking for the coordinate 672, the one that's poking out on the edge, and there is 672. So that's the graph of y equals 2x squared. Not very hard, because 2 36's are 72, hence y equals 2 lots of the x that's just been squared. Doesn't make, it's not hard, is it? Next one, well, that's going to be y equals 3x squared, because 3 36's are 108. And finally, y equals 4x squared is the most stretched one. Now I've got a Skype message here. I don't want to talk to Joanna because obviously I'm quite busy. I'll get to her later, so get rid of her. Right, so y equals 4x squared. Now let's see what's happened. Very easy to see actually. It's as though I've taken my x squared graph and stretched it up and stretched it up and stretched it a bit more. I've transformed it. So here's my generic transformations. Let's write it bigger. So y equals something multiplied by the original function x squared. Alright, and these somethings are the 2, the 3 and the 4. And as you can see, as I increase the value of a, it gets more and more and more stretched in the y direction. So here I go, 636. The x coordinate hasn't changed, but the y coordinate has. 672. The x coordinate hasn't changed, but the y has. 108. The x coordinate has not changed, but the y has. So essentially, the way you transform the graph is to leave the x coordinate unchanged, but multiply the y coordinate by the value, I was meant to say by, not ba, by the value of by a. So when a equals 2, for example, I go from y equals x squared transformed into y equals 2x squared, and my y coordinate of 36 gets multiplied by my a value, the 2. 2 36's are 72. Alright? And likewise, when I've got y equals 3x squared, my a in front of the function means multiply the y coordinate by 3. So 36 times 3 makes 108. And there it is. I've stretched it in the y direction, but the x values 6, 6, 6, 6 have not changed at all. So how else can I describe it? These are called, they're stretches, so it's a stretch in the y direction using a scale factor of A. So there we go. Right then, so if I'm going from 636 to 620, to 672, that will be a stretch in the y direction scale factor 2. But if I work on this side, it'll be easier to see. Whether I'm working with negative x values or not makes no difference, because the positive value of the x squared or the 2x squared, etc., will still be in the positive direction up the y-axis. So if I'm going from, I'll try and create a little arrow then in black. I'm going from 36 to 72. That's a bit thick there, just skinny it down a little bit. Going from 36 to 72, and that's clearly, it's a times 2 stretch in the y-axis, up the y-axis. So from 36 up to 72, I've basically multiplied the y part, the coordinate, by the a, and this a is times 2. And if I do it again from 36 up to 108, that represents a stretch of times 3 in the y direction. So it'll be a times 3 stretch in the y direction. I ought to have the word direction there. I better have the word direction here as well. Alright, so it's quite easy to see that the graphs are being stretched. If a is worth 2, multiply the y coordinate by 2 and replot all the points. If the a equals 3, multiply the y coordinate by 3, the new a value, and that will be a stretch of scale factor 3 in the y direction. So really this transformation AFX means stretch your graph in the y direction by multiplying the y parts of each coordinate by the value of a. So whether it be 2 or 3 or 4, and these are the transformations you would get stretched upwards. Okay, not too bad to see. Let's try the next little lot. Well, again, here's my generic y equals x squared, and this is my y equals minus x squared. Alright, please note I'm leaving the minus outside of the bracket, because if you square a negative number inside the bracket, it becomes positive again, and this is what we're going to get. Right, very easy to see what's going on. This is clearly y equals x squared. Just have a quick little proof there. 4 times 4 is 16, and that's probably the coordinate for 16. Again, I've not allowed the software to plot too many lines. If you read across there, it's gone above the halfway mark, it's about there, so it's 416. And look what's happened over here. I now have 4 minus 16. That coordinate's just there, as opposed to that one right there, which is 416. If I draw this a little bit bigger, we see we have y equals negative function of the x. Easy to describe? Yes, it is. It's simply a reflection in the x-axis. Alright? There's your x-axis, as you know. There's the y-axis. So this transformation is a reflection in the x-axis. Very easy to draw, very easy to see, and that's great. It's an easy transformation. So y equals minus function of the x, reflection in the x-axis. Alright? Let's try and get one more done in this video. Now look at this one. I'm not using y equals x squared anymore for one simple reason. I'm using y equals x cubed, which has got a beautiful shape. And here I've got the transformation y equals minus x, which has been cubed. Alright? Let's see what happens when I transform y equals x cubed. There it goes. Now, it's a different transformation. Let's just go back a little bit and just check again. Yep. Look at it very carefully. This is the function, or rather transformation, y equals function of minus x. It's not the same thing. It's not the same thing as y equals minus the function of x. Now, y equals minus the function of x was a reflection in the x-axis, wasn't it? Let's go back and check that. There it is. Y equals minus x squared, y equals minus x squared, and that gave us a very clear reflection in the x-axis. Please note the minus is outside of the function. Here we have x is within the bracket first, and then you apply the function and then you cube it. Alright, so here's me applying the function, and the function is y equals x cubed, so let's just write it as such. And if you look at what's happened to this purple little thing, it has an equation actually of y equals minus x cubed. What has happened? Very simple. This branch here has been reflected in the y-axis to produce this in the second quadrant, and this branch of the line y, or rather this branch of the function y equals x cubed, has been reflected again in the y-axis to produce this part of the function y equals minus x cubed, and that's in the fourth quadrant. Therefore, this function involves a reflection in the y-axis. Now, I'm glad I've got both these together, right? I've got this one I've just described as a reflection in the x-axis, and the function is y equals, the transformation is y equals f bracket minus x, but the function y equals minus f of x is a reflection in the x-axis, and they are different things, alright? Slightly different, but they produce wildly different results, alright? So there's the graph, y equals x cubed, reflected in the y-axis here, produces this beautiful purple arrangement of the equation or function y equals minus x cubed. It's lovely. Compare it with the other ones. Y equals x squared there, y equals minus x squared here, and I just better label it because I didn't do it. So that's y equals minus x squared. Beautiful, there it is. Minus x squared, y equals x squared. It's all about when you apply the function. So there we go, a reflection in the x is that one, and a reflection in the y is this one here. Alright, if you want to go back and look at the coordinates very carefully, how I constructed them, when x equals minus 36, x squared is clearly minus 6 times minus 6, which is positive 36. Alright, so that's straightforward. But then if you apply the function by putting a negative value in front of it, then you end up with minus 36, which is why 636 gets transformed into 6 minus 36, and there it is there. Okay, 6 minus 36, and that one of course is 636. Okay, mathematically, let's just go one more time. I'll take minus 6, square it, and then apply the function. Try it one more time. Let's do it with 3, shall we? 3, let's square it to make 9, then apply the minus function, and of course the effect is that here I've got 3 and minus 9, which is the mirror image of 3, 9 in the x-axis. Straightforward. Then of course this gets a little bit more difficult. Let's just try the cube graph. Let's go 2 for the x value, let's cube it and get 8, and so here I'm going to put, here I'm going to take my 2, do it this way, minus 2, and then cube it, and if I go minus 2 times minus 2 times minus 2, if you work that out, that will in fact give us minus 8. And that's exactly what we see here. Alright, so 2 gets transformed into minus 8, and the net effect of that is to produce reflections of the original function y equals x cubed as a reflection in the y-axis to produce the transformed version y equals minus x cubed, and there it is. It's beautiful, isn't it? Got to study this one. It's the trickiest one going so far. But I've got both of these two reflections. Remember, I'm getting all very serious about this now. Y equals minus f of x, reflecting the x. Y equals f of minus x, reflecting the y. And that's what we got. Better stop now, because it's going to get really, really heavy.